Uh, okay, good evening everyone. So today we are going to start our problem solving session for week 7. And in today's class we will discuss the problems on topic related to covariance, variance covariance matrix, correlation coefficient and conditional expectation. So before that I am just going to revisit all the formulas which were taught in the class, so it kind of a revision. So in first half we will go through all the formulas and then we will try to solve the questions. Okay. Okay, so first is the covariance. Okay, so let x and y be random variables such that second moment of random variable x is finite and second moment of random variable y is also finite. Okay, then the covariance between x and y is defined as covariance of x comma y is equal to expectation x minus expectation of x into y minus expectation of y, the expectation of this multiplication. This is the covariance between x and y. So there are few results related to this covariance, which is covariance of x comma y is nothing but expectation xy minus expectation of x into expectation of y. So this is by expanding this formula we will get this result. Okay, then second, there is covariance between x and y is equal to covariance between y comma x. Okay, so it is a quantity which shows that how this x and y differs from each other. Okay, so that's why this covariance of x comma y is equal to the covariance of y comma x. So it doesn't matter in which sequence we write these, the covariance will remain same. Third is that covariance between this same random variable is nothing but their variance. And fourth result is this covariance of ax plus b is nothing but a into covariance of x comma y. Okay, so this is ax plus b comma y. So if instead of x we will take ax plus b, where a and b are constant, then it is the a will come outside and we just find the covariance of x comma y. Okay, and b is a constant, so therefore this variance of b is 0 with respect to y. So the covariance of ax plus b comma y is a into covariance of x and y. And fifth result is if x and y are independent, then covariance of x comma y is equal to 0. But it does not implies that if covariance of x comma y is 0, then they are independent. This is not true. Okay, if x and y are independent, then the covariance will going to be 0 between x and y. But if the covariance between x and y is 0, this doesn't imply that they are independent. Okay, so the converse of this statement is not true. I hope this is clear. Now this is now we will discuss what is the. So these are for two random variables. So if let there are xn random variables, okay, then there is a covariance variance matrix which is defined as variance of x1, covariance of x1 comma x2, covariance of x1 comma xn. Then the second element will be covariance of x2 comma x1, second element will be variance of x2, and similarly covariance of x2 comma xn. And this last row's first element will be covariance of xn comma x1, and the last element will be variance of xn. So this is the variance covariance matrix for n random variables. This is covariance variance matrix. Okay, so now we will move to this correlation coefficient. This is denoted by rho x comma y. This is correlation coefficient for two random variables x comma y. This is nothing but covariance between x comma y divided by variance of x, root of variance x, and root of variance y. Okay, so this sigma x comma y, it will always be less than equal to 1. Okay, and covariance between same random variable is always 1, and covariance between ax plus b comma,
This is correlation coefficient, no?
yeah,
Covariance or
it's correlation coefficient.
Okay.
Yeah, and correlation coefficient between random variable ax plus b comma y, where a and b are constant, is nothing but correlation coefficient between x comma y. So this can be proved easily. I am not including the proof for this because we will solve some questions and then we will see how these two terms are equal. And if x and y are independent, then this correlation coefficient for x comma y is equal to 0, but converse is not true. Okay. So first I will take questions on this covariance and correlation coefficient, and if we had time we will move to the conditional expectation part. Okay. So this is the first question. So if x and y are independent and identically distributed random variables, then it is necessarily true that expectation of, okay, this is on conditional probability, so we will take this question after solving other questions, or maybe I will, okay, just wait. So I will just take this conditional part also, because first two questions are based on on the conditional probability, conditional expectation. So in the previous classes we have looked on the on finding the conditional probabilities and conditional distribution, and in this class we will see how to find the conditional expectation. Okay, so let x and y be two random variables. Okay, these are discrete random variables with joint PMF px comma y. Then conditional expectation PMF of x given y is equal to small y is so this PMF will be the probability that x is equal to x for y equal to y. Okay, so this is provided that probability y equals to y is greater than 0. So now this expectation is nothing but summation of x px. Okay, this summation is over y. Okay. So this will be a function of y. So this will depend on the values of y, because this conditional expectation is saying what is the expectation that for the random variable x, given that this random variable y takes value small y. Okay, so that's why this conditional expectation is different from the expectation of a random variable. This ex given y is different from expectation of x. Okay, because this depends on y and this is independent of y. So there are few results for conditional expectation. First is this conditional expectation. So I am denoting this conditional expectation of x given y equal to small y as this notation. So this is always greater than 0 if random variable x is greater than 0. Okay. Second is expectation for a constant value, say 1, given any random variable y is always equal to 1, because this constant value does not depend on random variable, it will always going to remain constant. Third is if x and y are independent, then expectation of x given y is nothing but expectation of x. Fourth is expectation of ax plus by given some random variable z is nothing but a into expectation x given z plus b into expectation y given z. Fifth, and this is the most important result, which is expectation of x given y is equal to expectation of x. So this is a very interesting result. So we will see the proof for this. So this expectation of x, so we can write it as this is for the this expectation. This is nothing but expectation of into fy dy. We write this outer expectation. So this is the function which is depending on y. So that's why I write this function, and we wrote this probability mass function for y, and it is and we are integrating it with respect to y. So this is for the outer expectation. Now we will open this inner expectation. So this will be open as if this is the conditional joint probability, this is for this expectation. This will be x fxxy into dx, and then this fy dy. Okay, so first we write the expectation for this outer expectation, where this was treated as a function. So we wrote this function as it is. And this is depending on y. That's why we wrote this probability mass function for y, and then it's dy. Then we opened this expectation part. So this is nothing but x fxy dx. Okay, so this after infinity minus infinity to infinity, and this is nothing but joint probability mass function of xy divided by probability mass function of y, and there is a probability mass function of y. This dx we will moving it backwards, this will cut, and then we got this minus infinity to infinity x joint probability distribution into dy dx. Now this is nothing. This joint probability distribution, when we are integrating it with respect to dy, we are moving this function inside. So this is nothing but f of x, because this is the joint probability distribution, and if we integrate it for the y, then we will get the probability mass function for random variable x. So from here we get x fx dx, which is nothing but expectation of x. Okay, so this is a very important result, that expectation of x given y is equal to expectation of x. Okay. Okay, so now we will solve the first question. So here it is given that x and y are independent and identically distributed random variables. Then we are asked that is it necessarily true that expectation of x given x plus y is equal to expectation of x divided by expectation of x plus y. So is this true or is this false? So what is your guess? What do you people think? Any guesses? Is it true or is it false? Just think about it, because this x and y, they are independent. So I think this is a simple question and you guys can solve it on your own. So you said false. Why you think it is false? Okay, so this question needs some more basics, so I will come again to this question. Okay, so for now we will solve few other questions and then I will move back to this question. So this is the second question. So let's this is email arrives one at a time in an inbox. Let Tn be the time at which the nth email arrives. Suppose that the waiting time between emails are independent and identically distributed with exponential distribution with parameter lambda. So this means that this so I will tell this again. Now each email is spam with probability q and non-spam with probability p, where q is equal to 1 minus p. Let x be the time at which the first non-spam email arrives. Then find the expectation and first arrival of non-spam email. Okay. So let y be the number of emails arriving. So we are given that inter-arrival time is IID with exponential distribution with parameter lambda. So this means that y is a Poisson distribution. So for Poisson distribution, the inter-arrival time is exponentially distributed with parameter lambda. So y is a Poisson distribution with parameter lambda. Okay. So here y is the number of emails arriving at a time. Okay. So which this follows a Poisson distribution with parameter lambda. Now it is given that a spam email arrives with probability q and a non-spam email arrives with probability p, which is equal to 1 minus q. Okay. So just a minute. So this is the first email arrive at, let's say, at time t plus 1, second email arrives at time t plus 2, third email arrive, fourth, similarly fifth email. ठीक है. Now these are all identically distributed with exponential random variable lambda. Okay. Now it is said that this email is either a spam or non-spam, and we know the probability that the email is spam is q, and probability that it is non-spam, it is 1 minus q, which is equal to p. So now let x is, so not x, let z be a random variable and it is sum of or what can I say? Okay, no. Suppose we have checked it for t plus n plus 1 time, so this will be the nth email. So given this n, for given n, the sum of total spam email, sum of all spam email is nothing but a binomial distribution with given n and with probability q. Okay, so from this n emails, how many of them are a spam email? So this will follow a binomial distribution with parameters n comma q. Okay, so also no, this okay. I just got confused. Just a minute. So let z so look at all these arrivals. So this, let's suppose this first email arrived. Now what is the probability that it will be a spam email? It is q, and it is a non-spam email, it is 1 minus q, that is p. So we can say that this event, that a spam email arrives, is nothing but it's a this Bernoulli distribution with parameter q. Similarly, this event of non-spam email is Bernoulli distribution with parameter p. Now given that these events are Bernoulli with some parameters q and p, now we can fix a value n, which is the n is the here this is the nth email. Okay, so we are saying that total n emails are arrived. So let's suppose total n emails arrived in some time capital T. Now let's suppose this z is sum of all spam emails and w is sum of all non-spam emails. Okay, so this z is summation so this z is sum of all spam emails. So this means this z follows a binomial distribution with given n and probability mass function q. So this distribution will tell us that out of n emails, how many of them are spam, given the probability of spam emails is q. Similarly, this W is binomial distribution with n comma p. This will tell out of these n emails, how many of the emails are non-spam, given the probability of non-spam email is p. Okay. So now we will So now we will find the probability of this z given some value n. So this we will find the probability of z for some value k. Okay, or we can say k z. Okay, so let's suppose it's a value k. So this is nothing but for all value of possible n, we will see what is the probability that x is equal to k, given that this capital N, which is the nth arrival, total number of emails. Okay, so the probability of z for all given n is probability that why I am writing x here. This z is equal to k, given that capital N is equal to small n, with probability mass function of this n. Now on solving this, we will get this is a binomial distribution. So for n comma k, this probability q to the power k into 1 minus q to the power n minus k, and this is this is Poisson distribution. We have seen this n is this let's take is this is n. There is a number of emails arrived in a given time period. So this follows the Poisson distribution. Okay, so that's why the probability that this Pn is taking the value small n is nothing but probability mass function for Poisson distribution, which is nothing but e to the power minus lambda. Lambda is the parameter for the exponential distribution, into lambda to the power n divided by n factorial. So now we will see on expanding this, we will get q to the power k, 1 minus q to the power n minus k, e to the power minus lambda to the power n divided by k factorial upon n minus k factorial, because when we open this, it will be n factorial divided by k factorial into n minus k factorial, so n factorials will get cancel out. Then we can write as at e to the power minus lambda q to the power k divided by k factorial. This is all constant, so this will come out of the summation, and this will become mu into 1 minus q to the power n minus k divided by n minus k factorial. This will become e to the this is lambda. E to the power minus lambda q to the power k e to the power lambda 1 minus q divided by k factorial, and this will get e to the power minus lambda q divided by k factorial. So we can see that this becomes a Poisson distribution with parameter. So this z is a Poisson distribution with parameter lambda into q. So this was nothing but total number of spam email arrived. Similarly, W is also a Poisson distribution with parameter lambda p, where W is total number of non-spam email. So here we saw that we have a random variable, Poisson random variable with a parameter lambda. We can split it into two Poissons, okay, if we know the probabilities for those two events given some p and q such that p plus q is equal to 1, then n1 can be a Poisson distribution with p lambda and n2 can be a Poisson distribution of q lambda. So this n is equal to n1 plus n2. Okay, so we, for a given Poisson distribution, we can split it into two Poisson distribution whose sum is equal to this actual Poisson distribution. Such only when these probabilities of these two events, the summation of these two probability of these two events is 1. Summation of probabilities of these two events is 1. Only then we can split this Poisson distribution into two separate Poisson distributions. Okay, and the parameters will become that probability into the parameter and the probability into the parameter, event probability into the parameter. So in this question we are said that each email is a spam with probability q and it is non-spam with probability p. So we are asked about the time at which the first non-spam email arrives. So we know that for Poisson distribution, we solved this in the previous class. For Poisson distribution, the first arrival...
You're not visible, ma'am.
Yeah, sorry. So for Poisson distribution, the first not the first, but the arrival time of nth arrival time of nth what can I say, or I can say the arrival time for Poisson distributions. Arrival time of Poisson for Poisson distribution follows gamma distribution with parameters n comma lambda. Okay, n means nth arrival. So what is Poisson? Poisson is that first element arrive, then second arrive, then third arrive. These have some time t1, t2, t3. So these t1, t2, t3, t4 and all, they are distributed according to gamma distribution with parameters. If we are seeing up to time tn, then for this n, this is distributed according to gamma distribution with parameter n comma lambda. So if we are seeing for only first, we are asked for the first arrival, then n is equal to 1. Okay, so expectation of this first arrival is first arrival. So we can say this event is a gamma distribution with parameter 1 because n is 1 and parameter lambda. So we know for gamma distribution the expectation is 1 upon lambda. This is n by lambda, but here the value of n is 1, so this becomes 1 upon lambda. Okay, but we are not asked about the first arrival time. We are asked the expectation of first non-spam email. So we saw that this non-spam email is Poissonly distributed with parameters lambda into p. So this let t1 be the event of first non-spam email. This t1 is gamma distributed according to gamma distribution with parameters 1 comma lambda p. So expectation of t1 will be 1 upon lambda p and variance will be 1 upon lambda p whole square. This is from gamma distribution. Okay, so we are given in the question that emails arrive one at a time in an inbox and tn be the time at which the nth email arrives. Suppose that waiting times between emails are IID with exponential distribution with parameter lambda. So with this statement we can conclude that this arrival of emails is a Poisson distribution. Okay, now they say that each email is a spam with probability q and it's a non-spam with probability p and p plus q is 1. So we have a Poisson distribution with parameter lambda. Okay, and now we can split that this Poisson distribution, the one Poisson distribution, into two small Poisson distribution, which one of them is indicating the arrival of spam email and another one is indicating the distribution of arrival of non-spam emails, and those both are also Poissonly distributed but with different parameters. One is with parameters lambda into the probability of that event and another will be the same. Okay, So we have a Poisson distribution with parameter lambda. Now we have we can split this Poisson distribution into two other Poisson distribution depending on the events, depending on event probabilities. So this is the Poisson for spam email. So this is with the parameter lambda into p. This is non-spam, sorry. And Poisson distribution for spam email with parameter lambda into q. Okay, so we split our actual Poisson distribution into two different Poisson distribution, and summation of these two is our actual Poisson distribution. Okay, and now we wanted to know the expectation of arrival of first non-spam email, and we know that arrivals of Poisson distributions are gamma, will generate a gamma distribution with parameter this sorry this T1 is gamma distribution with parameter 1 comma lambda p. So expectation of T1 is 1 upon lambda p and variance is 1 upon lambda p square. So it is a quite interesting question where we just from one statement we figure out that this is a Poisson distribution and that we can split the Poisson distribution into two with the event probabilities, and these two distribution are also Poisson with some different parameters. And then we saw that the arrival of this first Poisson distribution is gamma distributed, and then expectation of first arrival can be 1 upon lambda p and variance can be 1 upon lambda p square, which is the property of gamma distribution. So in this question we covered a lot of concepts of whatever we have studied till now. So it's a very good question, and if you don't understand, please revisit this lecture and try to understand this concept. So it is a quite important concept. So now we will move to the next question. So we have two fair six-sided dice, and one is green and one is red, and we rolled them, and outcome of x and y, uh, so outcome of green dice is x and outcome of red dice is y. Now we want to find what is the covariance for x comma y, x plus y comma x minus y. Okay, so just give me a minute. So x is outcome of green dice and y is outcome of red dice. So what are the possible outcome? 1, 2, 3, 4, 5, 6. And what is the corresponding probabilities? 1 by 6, 1 by 6, 1 by 6. So this is true for both x and y, right? This is the small value x. and these are the corresponding probabilities for this. So from this we can find the expectation of x, which is nothing but 1 into 1 by 6 plus 2 into 1 by 6 plus 3 into 1 by 6 plus 6 into 1 by 6. This is nothing but 3.5. Similarly, expectation of y is also 3.5. Okay. Now x and y are independent random variables. Independent because these are outcomes of two separate dices. Okay, so they are not dependent on each other, they are independent. So this for calculating the expectation of x plus y, we can write it as expectation of x plus expectation of y. Similarly, expectation of x minus y is expectation of x minus expectation of y. So this will be 7 and this will be 0. Okay. Now we need to find the covariance between x plus y into x minus y. So we know that this is nothing but expectation of x plus y into x minus y minus expectation of x plus y into expectation of x minus y. Okay, this is from the property that covariance of x comma y is expectation xy minus expectation of x into expectation of y. So using this property, we wrote this. But we wrote that covariance of x plus y, expectation of x plus y into x minus y minus expectation of x plus y into expectation of x minus y. So this term is 0, so this will whole become 0. Now we just need to find the expectation of x square minus y square. So this is nothing but expectation of x square minus expectation of y square. So now expectation of x square is nothing but sigma x square px, so which is 1 into 1 by 6 plus 4 into 1 by 6 plus 9 into 1 by 6 plus 36 into 1 by 6. So this will come out to be 91 by 6. Similarly, expectation of y square is also 91 by 6. So therefore, this covariance of x plus y comma x minus y, which is expectation of x square minus y square, is nothing but 0. Okay. So now we will move to the next question. I hope this you guys understand this part. So now moving on to the next question. So this is a very simple question and we have discussed this question in class a lot of time. So I am not going to solve this question, and I will ask you guys to solve this. And if you have any doubt in this question, we can discuss it in the next class. So I will move on to this, but please try this question. This is a very good question. So answer for this is 1. Or if you want to try it now, we can. Okay, let's solve this question. So we are given this for x less than 0, and for x greater than 0 it is e to the power minus x by 2. So we can make a function, and what we have asked the expectation of mod x. So x is a random variable with this uh, if with this probability density function. So this mod x, for this mod x, what we can write, what will be the probability distribution function for this mod x. So if you can see precisely, you can conclude that this mod x, this probability mass function for mod x is nothing but e to the power minus x by 2. Okay, where this mod x is greater than 0. So if this x is negative, then it will open with a negative sign, and this will become e to the power x by 2. And if x is positive, then it will open with the positive sign, so it will remain e to the power minus x by 2. So the probability mass function for mod x is nothing but e to the power minus x by 2. Okay. So now this expectation for mod x is nothing but x into mod x minus infinity to infinity into dx. So for okay, x e to the power minus x by 2, or this is mod of dx, right? So now when you solve it, so now when you open this for x greater than 0, this will come as positive, this dx, this d mod x will be dx, and when x is less than 0, this d mod x will be minus dx. Okay, so this is also mod x, and this is in the mod form, and this is d of mod x. So this is nothing but minus e to the power minus mod x into mod x plus 1. We open this. This is from minus infinity to infinity. So for minus infinity to 0, it will open as this minus x plus 1. From minus infinity to 0 plus e to the power, this will be positive, sorry, this will be minus x plus 1 from 0 to infinity. So on solving this, this will be 1 divided by 2, because this is nothing but mod x e to the power minus x by 2 d mod x. So this will become 1 by 2 plus 1 by 2, which is equal to 1. So this value is 1. So now we move to the next question. So now suppose that x and y have a joint PMF as shown in the figure, Now this mu x is 3 by 2, mu y is 2. So these are the expectation of x is 3 by 2, expectation of y is 2, standard deviation for x is 1 by 2, and standard deviation for y is root 1 by 2. Then we need to find the correlation coefficient of x and y. Okay, so this mu x is 3 by 2, mu y is 2, sigma x is 1 by 2, sigma y is. So this is given. We have asked this correlation coefficient of x and y, which is nothing but covariance of x comma y divided by variance of x into variance of y. Okay, now so we need to find this covariance of x comma y is nothing but expectation of xy minus expectation of x into expectation of y. So expectation of xy will be nothing but expectation xy into probability joint probability mass function for f x comma y, which is given in the question, and minus mu x mu y. These expectations are also given. So from the table we can see for f1 comma 1 the probability is 0.25, for f1 comma 2 it is 0.25, for f1 comma 3 this is 0, for f2 comma 1 it is 0. So we can write this expectation of xy, we can write it as summation xy x into, this is the function and this is the probability mass function for x comma y. Okay, so this is 0.25 0.25 0 0 0.25 0.25. So this is the probability mass function for x comma x, joint probability mass function for xy. So we can write for 1 comma 1, so x and y are 1 into 0.25 plus 1 into 2 into 0.25 plus 1 into 3 into 0 plus 2 into 1 into 0, because this is x into y into the probability of probability for that x and y. Okay, so for 1 comma 1 x is 1 y is 1 and probability is 0.25, that's why this is 1 into 1 into 0.25. For 1 comma 2 the probability is 0.25, so again the x is 1, y is 2, and this joint probability is for 1 comma 2 is 0.25, so we wrote 1 into 2 into 0.25. Similarly for 1 comma 3 and 2 comma 1, and for this 2 into 2 into 2 into 0.25 and plus 2 into 3 into 0.25. So this will come out to be 13 by 4. Okay, so now this is expectation xy. So covariance of x comma y is expectation of xy minus expectation of x into expectation of y. This is 13 by 4 minus expectation of x is given 3 by 2 and expectation of y is given 2. This is 3. So 13 minus 12 by 4, this is 1 by 4. So correlation will be covariance divided by variance of x and variance of y. So this is nothing but this covariance x comma y, sigma x sigma y, because sigma x square is variance, sigma y square is variance, so root of variance will be sigma x and sigma y. So now this is 1 by 4, sigma x is given in question, which is 1 by 2, and sigma y is given as root 1 by 2. So this value will come out to be 0.71. Okay. So I hope the solution is clear. So now we move to the next question. So let's suppose that I roll a die, a fair die. A fair die. Okay, so it is just a minute. So we roll a fair die n times and let x be the number of ones that I observe and let y be the number of twos that I observe. So then I need to find the covariance of x comma y and correlation between x comma y. So yeah. So we can say this x is number of ones, okay, we observe when we roll fair dice n times, and y is number of twos we observe when we roll the fair dice n times. So we know the probability when we roll a dice. What is the probability that its outcome will be 1? It will be 1 by 6. And we have said that x is the number of ones that appears when we roll a dice for n times. So this can be x can be seen as the let's suppose if success is defined as when outcome is equal to 1, okay, so probability for this event is probability of this event is 1 by 6, okay, and we consider this event as success. So we can say that x is a binomial distribution when we roll the dice n times and the probability of success is 1 by 6. Similarly, y is also a binomial distribution when we roll our dice n times and probability that we will we get our outcome as 2 is also 1 by 6. Okay, so x and y both are binomial distribution. So now variance of binomial distribution is np into 1 minus p, where p is rate of success, probability of success. So variance of x plus y can be written as n into p probabilities n into p into 1 minus p plus n into q into 1 minus q. This is for x, this is for y. So this is n into 1 by 6 into 5 by 6 plus n into 1 by 6 into 5 by 6. Okay, so this will be n into 2 by 6 into 5 by 6. All right. Okay, wait. Just a minute. This x is a binomial distribution with n comma 1 by 6, and y is also a binomial distribution with n comma 1 by 6. Now this x plus y is also a binomial distribution for the same n, and this probabilities will be add up and becomes 2 by 6. So this x plus y is number of ones and twos that will appear in the system if we roll a fair dice. Okay, so the probability that we will get either 1 or 2 will be 2 by 6. So that's why this x plus y can be written as a binomial distribution for n trials, and where the success probability is 2 by 6, because here the success probability is that we will receive either 1 or 2. Okay, so this x plus y is a binomial distribution with parameters n comma 2 by 6. Okay, so now variance of x plus y is n into, the success probability is 2 by 6 into 1 minus success probability. This is from the binomial distribution formula. And it is also known that variance of x plus y is nothing but variance of x plus variance of y plus 2 into covariance of x comma y. So we know this is n into 2 by 6 into 4 by 6. We know that variance of x is n into 1 by 6 into 5 by 6. Similarly, variance of y is n into 1 by 6 into 5 by 6 and plus 2 into covariance of x comma y. So we get thus, so from here we get that covariance of x comma y is nothing but,
How it's 4 by 6?
so for binomial distribution, if binomial distribution has parameter n comma p, then its variance will be given by n into p into 1 minus p. So p is given as 2 by 6, therefore 1 minus p is 4 by 6. Okay.
Okay.
So covariance of x comma y from that previous equation, we will get it as minus n by 36. So covariance is minus n by 36, and now we need to find the correlation this correlation coefficient. So this correlation coefficient is nothing but covariance of xy divided by variance of x into variance of y, root of variance of x into y. So this is minus n by 36, and this is minus n by 36. This is root of variance of x is n into 1 by 6 into 5 by 6. Similarly, variance of y is also the same, 1 by 6 into 5 by 6. So we can see this will be 1 by 36 into n into 5 into 36. This will cancel out and the covariance will come minus 1 by 5. Correlation coefficient will come as minus 1 by 5. Okay. So I hope this is clear.
Yeah.
Okay. So moving to the next question. So we are given that this x and y are two jointly continuous random variables. Two jointly continuous random variable with joint PDF given as fxy is 2 when x plus y is less than 1 and x and y both are equal to 0, and it is 0 otherwise. Now we need to find the covariance and correlation coefficient for this function for these two variables. So we are given this joint probability distribution. This is 2 when x plus y is less than equal to 1 and x is greater than 0 and y is also greater than 0, and it is 0 otherwise. So now we find, first we will find the f of x, then we will find the f of y. Okay, then we will find variance of x, variance of y, and from there we will find this covariance of x comma y and correlation of x comma y. Okay, so let's see. So f of x will be joint probability mass function integrated for whole y from minus infinity to infinity. So this y can maximum goes from 0 to 1. So for 0 to 1, this is going to be, this probability mass function is going to be 2. So for y from 0 to 1, or not, for this f of x is joint probability mass function into dy, and where y is varying from minus infinity to infinity, but we are given that this is equal to 2 when this y is varying from 0 to 1. Okay, or this y, wait, x plus y is less than 1, then this is equal to 2, right? So okay, let's suppose x varies from 0 to 1. Okay, now this f of x, this can be written as that y is varying from 0 to 1 minus x. Okay, because we want fx, so we want it in terms of x, we integrate it with respect to y. So this is 2 into dy from 0 to 1 minus x, so it will come out to be 2 into 1 minus x. Okay, so thus f of x is 2 into 1 minus x when x is varying from 1 to 0, and it is 0 otherwise. Similarly, f of y will come out to be 2 into 1 minus y when y is between 0 to 1, and it is 0 otherwise. Okay, so expectation of x is x into fx dx, where x is varying from 0 to 1, so this will come out to be 1 by 3, and similarly expectation of y is also 1 by 3. Okay, now expectation of x square is nothing but x square fx dx from 0 to 1, so this will come out to be 2x square 1 minus x dx 0 to 1, so this comes out to be 1 by 6. So variance of x is expectation of x square minus expectation of x whole square, so this will come out to be 1 by 18. This is come out to be 1 by 18, and similarly expectation of y is also 1 by variance of y is also 1 by 18. So we found that expectation of x is equal to expectation of y is equal to 1 by 3, variance of x is equal to variance of y is equal to 1 by 18. Now we know that covariance of x comma y is expectation of x y minus expectation of x into expectation of y. So this expectation of xy is nothing but x into y into joint probability mass function of this joint distribution of x comma y into dx dy, where x and y are varying from 0 to 1. So this is 2xy dx dy 0 to 1, this will come out to be 1 by 12. So this covariance is expectation xy minus expectation x expectation y. This is 1 by 12 minus 1 by 3 into 1 by 3. This will come out to be minus 1 by 36. And this correlation will be covariance of x comma y divided by variance of x into variance of y. Covariance is minus 1 by 36. This is 1 by root 1 by 18 and root 1 by 18. This is minus 1 by 36 into 18. So this comes out to be minus 1 by 2. And covariance is okay. So I hope this is clear. So now we will move to the next question. So in this problem we will see that how this covariance coefficient is always varies from minus 1 to 1. So the mod of correlation coefficient is less than equal to 1, so which means that this correlation coefficient is varying from minus 1 to 1. So the by definition of this covariance of xy is just a minute. Okay, so it is given that rho of this correlation of x comma y correlation of x comma y is equal correlation coefficient of xy is equal to covariance of u comma v, where u and v are the normalized version of x comma y. So u is x minus expectation of x upon standard deviation of x, and similarly v is y minus expectation of y upon standard deviation of y. So now we need to show that this rho of xy is always less than equal to 1. Okay, so what we have that variance of this u is x minus expectation of x upon sigma x. V is what? Y minus expectation of y upon sigma y. Okay, now we know that variance of u plus v is nothing but variance of u plus variance of v plus 2 into covariance of u comma v. Okay, so variance of u so this is the normalized version of x. So this means that u is a normal distribution with with the sorry just a minute, mu comma 1, right? this will be 0 comma 1. So this is the normalized version of x, so which means that this uniform distribution u is a normal distribution with the mean 0 and variance with standard deviation 1. Okay, in the question it is given that this u and v are normalized version of x comma x and y, as u is x minus expectation of x upon sigma x and y is y minus ey into sigma y. So this give us that, just a minute. This means that u is a normal distribution with parameter 0 comma 1 and v is also a normal distribution with parameter 0 comma 1. So variance of u plus v is nothing but variance of u plus variance of v plus 2 into covariance of u comma v. So this is nothing but 1 plus 1 plus 2 into rho xy, because it is given in the equation that covariance of u comma v is rho xy. Okay, so we replace it, covariance of u comma v as this rho xy. Okay, this is this. Now we know that this variance of u plus v is greater than equal to 1. Okay, as u and v are both normally distributed with mean 0 and variance and with standard deviation 1 and variance 1, so we know that variance of u plus v is greater than equal to 0. So this implies that 2 plus 2 rho xy is always greater than equal to 0, which means that xy is always greater than equal to 1. And okay, from this it can be concluded. And also we can say that this minus, if we take this as minus x, rho of minus x, it will also equal to minus 1. It is greater than minus 1. Okay, so if we so if you have taken u as a minus x, okay, minus x, then we have taken the expectation of minus x and sigma of minus x, then also this result will follow that rho of minus x comma y is also greater than equal to minus 1. But rho of minus x comma y is nothing but minus of rho xy. In the start of lecture we saw this relation. So therefore this rho of xy is always less than equal to 1. Okay. So just try to go through this proof again after this class is over, and then you will get an idea, because we are using very different properties from normal distribution, and then we are using the relations for this correlation coefficient, so everything is getting mixed up. So you need to revise these lectures after these sessions to understand them better. So now we will move to the next question. I hope we have done here. Okay. So now let x and y be two independent uniform random variables. Let also that z is equal to maximum of x comma y and w is equal to minimum of x comma y. Now we need to find the covariance of z comma w. So in the last classes we have seen what will be the distribution of z, which is equal to maximum of x comma y, and w, which is the minimum of x comma y. So in this class we also see those things. So let's this x is uniform and y is uniform. Z is maximum of x comma y, and w is minimum of x comma y. Now we will find the distribution of z, which equal to probability z is less than equal to z, which is probability maximum x comma y is less than equal to z. So this means that probability, if maximum of x comma y, if maximum of between x comma y is less than z, this means that if x is greater than y, okay, suppose maximum of x comma y is x, let maximum of x comma y is equal to x. So we are in here, we are saying that if x is less than z, so this means that y is also less than z, because maximum between x and y is x. So if maximum is less than something, then the number which is lesser than that is also less than that number. So it is nothing but probability that x is less than equal to z and y is less than equal to z. So now these two are independent, so probability is, this probability will become this. So this is nothing but probability mass function of x into probability mass function of y. Okay, so we concluded that this f of z is nothing but it is 0 when z is less than equal to 0, not equal to, less than. It equal to z square when z is varying from 0 to 1, and it is 1 for z is greater than 1. Okay, you can find this because it is, so when you put, so I think this is clear. So this fz is nothing but 2z when z is varying from 1 to 0, and it is 0 otherwise. So from here we can find the f of z, expectation of z, which is nothing but z into fz from 0 to 1. So this came out to be 2 by 3. Okay, so this is 2 by 3. Now so we need to find now the probability, this probability mass function for w. So this is nothing but pw less than equal to this. W is minimum of x comma y less than equal to w. So we can write this as 1 minus probability that x is greater than w and y is greater than w. So why 1 minus p? Because when we are taking the maximum, we just write it as x less than w and y less than w. But for if minimum of x comma y is less than w, this means that there is a chance that the let's suppose if minimum of x comma y is x, okay. So if this x is less than w, then we cannot say that this y is less than w. This y can or cannot be less than w. It can be greater than equal to w also. But so this but we know that one of them should be less than w, okay. So this probability is nothing but it is the 1 minus the probability that if any of them is greater than w, then uh, this won't hold. So this is the complementary function of this event. This is the complementary probability for this event, this event, okay. So that's why we wrote this. So now this is 1 minus probability x is greater than w, as these are both independent events. Y is greater than w. This is 1 minus probability that x is less than equal to w, and 1 minus probability that y is less than equal to w. So these can be written as 1 minus fx w, 1 minus fy w. So this comes out to be 1 minus fx w, 1 minus fy w. This comes out to be fx w plus fy w minus fx w into fy w, okay. So we can find that this fw is, it is 0 when w is less than 0, and if it is varying from 0 to 1, so this fx will be sorry, these are uniform now. So this will come out to be, this will be w, this will be w, okay, because x and y are uniform distribution, and uniform distribution, this is nothing but w. So this will be 2w minus w square when w is varying from 0 to 1, and it will be 1 when w is greater than 1, okay. So from here we can find this probability density function for w. So this will be 2 minus 2w when w is between 1 to 0, and it is 0 otherwise. Now from here we can find that expectation of w is w f w dw 0 to 1. So this will come out to be 1 by 3. Now we can easily find the covariance between z and w, which is nothing but covariance zw minus expectation of z into expectation of w, okay. So this expectation of z comma w, so So z is maximum of x comma y and w is minimum of x comma y, and this is z e w. This is multiplication. So we know that this for this covariance, if there is some ax comma y, it will be a into covariance of x comma y, and if there is any function, then we can write covariance in terms of this expectation of x comma y. This z in zw can be written as expectation of x comma y. Minus expectation of z into expectation of w. These are independent events, so it can be written as expectation of x is 1 by 2, expectation of y is 1. As x and y are independent events, this is 1 by 2 into 1 by 2 minus e of z is 2 by 3, expectation of this is 1 by 3. So 1 by 4 minus 2 by 9. This is 1 by 36. So now we will move to the next question. So let x and y are jointly normal random variables with parameter 0, 1 and mu y is minus 1 and variance is 4, and covariance is also given as minus 12. Now we need to find the probability that x plus y is greater than 0, and all these three questions. So we are given that x and y are jointly normal random variable with parameters as this mean of x is 0, sigma
Not visible.
oh sorry this x and y are jointly random variable, mu x 0, sigma x square is given as 1, mu y is minus 1 and sigma y square is 4. Okay, and this correlation coefficient is given as 1 by 2. Now this x and y are jointly random variable, therefore this u, which is equal to x plus y, is also a normal distribution. Okay, so this expectation of u is nothing but expectation of x plus y, and this is expectation of x plus expectation of y. So it is 0 plus minus 1, which is minus 1. Variance of u is equal to variance of x plus variance of y plus 2 into covariance of x comma y. U is x plus y. So variance of x is 1, variance of y is 4, and this covariance is 2 into covariance of x comma y. This is 5 plus 2 into covariance of x comma y. Covariance of sorry, the sigma xy is equal to covariance of x comma y upon sigma x sigma y. So covariance of x comma y is sigma xy sigma x gamma x gamma, sorry, rho xy is sigma x into sigma y. So covariance is equal to, this is given as minus 1 by 2, rho x is 1 and rho y is 2, because rho y square is given as 4. So this comes out to be minus 1. So this variance of u is 5 plus 2 into covariance x comma y, 5 minus 2, this is equal to 3. So this u is normally distributed with mu minus 1 and variance 3, sigma square 3. Okay, now we need to find that probability that this u is greater than 0. So this will be nothing, or this is distributed, normally distributed from minus 1 to 3, so we can easily find this probability. Okay, so I am leaving it to you, it's an easy part. So now we will move to the next part of the question, where we need to find the constant value of a if we know that ax plus y and x plus 2y are independent. Okay, so we know that ax plus y and x plus 2y are independent. So these are independent, this means that this covariance between these two elements is 0. Okay, from the properties of covariance. So we can write this covariance of ax plus y comma x plus 2y. So this will be, for first elements it will be a into covariance of x comma x plus a 2a into covariance of x comma y. We are just taking covariance for each element. So first x comma x, x comma y, there are few constant. So for first element we have taken a outside, a as a is constant, and then taken the covariance of x comma x. Then we taken this covariance of ax with 2y. So this 2 and a are constant, so they came outside, and this is covariance of x comma y. And then additional covariance of y comma x plus 2 into covariance of y comma y. So from here we will get this, this is a into variance of x plus 2a plus 1 into covariance of x comma y plus 2 into variance of y. So variance of x is 1, so a plus, this is covariance of x comma y, we found out this is minus 1, so this is minus 2a minus 1, and covariance of y is 4, so 2 into 4 is 8 plus 8, this is equal to 0. So 0 is equal to minus a plus 7, so a came out to be 7. So now the third part, we need to find the probability that x plus y is greater than 0 given that 2x minus y is equal to 0. So what we need to find, that probability that x plus y is greater than 0 given that 2x minus y is equal to 0. So let u is equal to x plus y as we considered earlier, and let v is equal to 2x minus y. So these x and y are normal distribution, so u and v are also a normal distribution. So So this u is normally distributed with -1, 3, and this v is normally distributed with mean 1 and variance 12. You can find it easily. So now let's find the covariance between u comma v. Okay, so this will be nothing but just a minute. Okay, so I haven't discussed this thing in the class. So this question I will discuss in the next class, because in next week I think professor will discuss more about this normal variate distributions. So here there are some properties that I need to use, but I need to, that are not discussed in the class, so we cannot solve this question right now. So I will discuss this question in the next class. Okay, so I hope everything is clear so far. Okay,
I have to go through the problems, that's all.
yeah. So in the next class we will discuss the first and the last question. Okay, because now
Okay.
the time has exceeded.
It's okay, no problem.
Yeah, okay.
Thank you.
Okay, thank you.